for Labor Day. Is that the right one? Labor Day, I always confuse those two. No school Monday. It's Labor Day. And because there's no school Monday, and because we can't do labs on Monday, there are no labs at all next week for anybody. I will be in the lab room during the lab periods, so if you have questions about homework or whatever, you can think of it as sort of like an office hour. Come on in and I can answer questions, but you don't have to be there. But I will be there if you have questions. And then the last thing is the quiz today. In the last 15 minutes of class, we're going to do the first quiz. No. Yes. No. Any questions about those 3 bullet points? Yes. Yeah, it's going to be mostly just short answer questions about stuff I've emphasized in lecture. But there are also, on average, there's going to be like one question that was assigned. It's going to be like exactly a question that you've done if you've been keeping up with the homework. So that's what's on it. I think it'll usually be 4 questions about the lecture and then 1 problem that you've done. Question? So before we go on to new stuff, does anyone have any questions on homework you'd like me to go over? I'd be happy to do a couple problems. I know those, for most people, most years, getting used to those kind of problems where somebody, like somebody goes from the house to the car and blah, and you choose the 0 position and the positive direction. Making sense out of those can be sort of tricky, but I think it's an important thing to sort of wrap your head around, so I'd be happy to spend some time on those if you'd like. Yes? Oh, yeah, you should not, I should not have assigned that one. We haven't even talked about velocity yet. Sorry about that. So skip the part about velocity for now. Okay, yeah, let's make one up and do it. Okay, so let's say that here's the shore. Okay, example. So here's the shore, here's the lake. There's a raft out in the lake. And a buoy. And this guy's standing on the shore. He doesn't have arms. That's water. And let's say it's 20 meters from the shore to the raft, and then 10 meters from the raft to the buoy. Let's say that the man starts on the raft, swims to the buoy, and let's say, how long does it take to swim 20 meters? Like 30 seconds? Then he swims back to the raft in 40 seconds. He's getting a little tired. Oh no, that's 10 meters. He's just a slow swimmer. And then swims back to the shore in 1 minute. 60 seconds. Okay, so let's say we want to plot a position versus time graph. First, let's say that the 0 position is on the shore. And the positive direction is towards the buoy. And then we'll do it again, but this time we'll make the 0 position at the raft and the positive direction toward the shore. So the first thing I'm going to do is draw a figure that just lets me visualize the whole motion. So so this is like the whole path, and I'm going to have this represent the shore. This is the raft. This is the buoy. Raft. And then it's 20 meters between the shore and the raft, and 10 meters between the raft and the buoy. And now I'm going to show his motion along this line. So what does it say he does? He starts out on the raft and goes to the buoy in 30 seconds. So he starts here, and it takes 30 seconds for him to get here. So I'll write that as 30 seconds. The path from this dot to this dot is 30 seconds. And then he comes back to the raft in 40 seconds. And then from the raft, he goes back to the shore in 60 seconds. Okay, so everything that's on this picture right now is totally independent of a choice of 0 position and positive direction. This is just, no matter where you're looking from, what you want to call the 0 position, what you want to call the positive direction, this stuff is just undeniable for anybody. Okay, And so you can think of this as like just a visual representation of the problem. And now for part A, it says we're going to choose the 0 position to be on the shore and the positive direction toward the buoy. So now I'm going to, all the stuff I do in red, I'm going to include the choices of the 0 position and the positive direction. Let me save this for later. So I'm going to use this same figure again for B. Okay, so the 0 position is the shore, and the positive direction is this way. So if the raft is 20 meters in the positive direction from 0, then what's the numerical label for the raft? 20, yep, positive 20. And if the buoy is another 10 meters in the positive direction, what's the numeric label for the buoy? Yep, plus 30. And so now all of these locations have numeric names. Okay? And that doesn't change what the swimmer does. The swimmer, just because we made this the 0 position doesn't mean the swimmer starts there. The swimmer still does this. Okay? So at what we're going to call the 0 time, I forgot to say anything about when the 0 time is. So let's just say that for A and B, 0 time is when he starts swimming. Okay. So at 0 time, he's at the raft, which has the value 20. 30 seconds later, he's at the buoy, which has the value 30. 40 seconds after that, he's back at the raft, back at 20. And then 60 seconds after that, he gets to 0. So position versus time graph. Position is always on the vertical. Time is always on the horizontal. The times that are going to matter are, well, let's say, if we're calling our time equals 0 the instant that he starts swimming, then he's at this, this instant here is represented by 0 time. So I'm just going to label this point 0 seconds. And then 30 seconds after 0, what would be the time value when he's on the buoy? Question? Oh yeah, I went back up. I'll go back down in a second. I'm just writing the time values on here. Okay, so what's the time value at the buoy? 30. And then 40 seconds after 30 seconds, what's the time value? Yeah, 70. And then 60 seconds after that, what's the time value? Yep, 130. Okay, so now we can just read all these values and put them on here. The times that matter are 0 seconds, 30 seconds, 70 seconds, and 130 seconds. And then the locations that come up, the only position values that I have written up here are 0 and 20 and 30. So I'm going to label those 0, 20, and 30. So at the time 0 seconds, what's the position? 20, yep. At the time 30 seconds, what's the position? Yep. At the time 70 seconds, what's the position? back to 20. And then at 130 seconds, what's the position? 0. Yep. And then, you know, connect these. So it looks something like that. Any questions about that? So now let's do it again for part B with the different choices, 0 position and positive direction. So I'm going to start with this picture again. So remember, this picture is totally independent of any choices. And now we're going to indicate the choices that we do make for part B on this figure. So for part B, it says this time the 0 is at the raft and the positive direction is toward the shore. Well, let me do the times first. Those aren't going to change. This is still 0. This is still 30 seconds. This is still 70 seconds. And this is still 130 seconds. Okay, well, if the raft is the 0 position, then we'll label that with a 0. And the positive direction is toward the shore, so that's positive. So to label the shore, what position are you at if you go 20 meters in the positive direction? Positive 20. And now this time, this is a little different. For the label of the buoy, we went 10 meters in the negative direction. So what's the label of the buoy? Negative 10.
If that's the positive direction, why is it negative 20?
That should say positive 20, you're right. Thank you. Okay, so now I'll draw the position versus time graph. So there's position, there's time. The time values that matter are 0, 30, 70, and 130. And the positions that matter are 0, negative 10, and positive 20. Okay, so when time is equal to 0, the swimmer starts on the raft, so what's his position? 0, yep. So a time equals 0, position is 0. Then at 30 seconds, what's his position? Negative 10. At 70, what's his position? 0. And then at 130, what's his position? 20, yep. And you can connect these. And now if you compare those two graphs, you can see they're shifted up and down from each other. What caused those graphs to shift up and down from each other? Yeah, the choice of the 0 position makes them shift up and down. They're not shifted left to right. What would have made them shift left to right? Yeah, a different choice of time equals 0. And then they're flipped from each other. What made that happen? Switching the positive direction. So, you know, we had the positive direction going out to the middle of the lake the first time and back toward the shore the second time, and that flipped them upside down. Any questions about that one? Okay. Well, we're just defining the kinematic quantities right now. We talked about position and displacement and distance. So the next thing we have to define is velocity. And does velocity have direction associated with it or not? Yep, it does. Pretty much all the ones that are important to us in this class do have direction associated. What's the non-directional quantity that's similar to velocity? Speed, right. So we'll talk about velocity, and I'll talk about how speed relates to it. And talking about velocity, I'm going to do it in two pieces. I'm going to first talk about average velocity. And for average velocity, you need to specify two instants of time, like a start of your interval and an end of your interval. So this is the average velocity from, like a time t1 to a time t2. And then after average velocity, I'm going to talk about instantaneous velocity. And instantaneous velocity is defined at a single instant in time. So I'll just say time t. And I guess the thing to keep in mind as I'm doing this, essentially all we care about in this class, the only velocity that matters to us is instantaneous. But in order to try to give you a sense of what instantaneous velocity is, I have to start with average velocity. So I'm just going to define the average velocity as kind of a stepping stone. This one we won't use much. Okay, so first, the average velocity. So we're going to choose two instants, T1 and T2. And then the average velocity from T1 to T2 is, I'll call it V average, and it's equal to the position at the later instant, so the position at T2, minus the position at the earlier instant, so position at T1, divided by the elapsed time, so divided by T2 minus T1. Another way you can think of it is it's the displacement from T1 to T2 divided by the elapsed time, the change in time. So if you start and end at the same, so if you choose your T1 and your T2 to be instants where you're at the same location, okay, you could walk 1,000,000 miles in between, but your displacement is always going to be the same. What would it be if you start and end at the same spot? It's always going to be 0 because all you're doing is subtracting the two positions, and if they're the same, they cancel out. And so that means that if you're taking an average velocity between two instants where you're at the same location, your average velocity is always going to be 0 too. Because if you have a 0 displacement, this ratio is 0. So, like, how many of you ran track in high school? Okay, how many of you only ran 200 meters? Okay, so everyone here, when you did any event, oh, how about 300-meter hurdles? Okay, you're disqualified. Everyone else. So any event where you start and end in the same position, right? You all had the exact same average velocity in every race. Isn't that amazing? It's like such a coincidence. You had a better average velocity than everyone else because you ran the 300-meter hurdles and you started somewhere different than you. In my head, I pictured that being funnier. Okay, so that's the average velocity, and let's think about what it looks like on a position versus time graph. Okay, so position is on the vertical, time is on the horizontal, and let's say that this is the function of position over time. And let's say that this is the instant we choose for T1, and this is the instant we choose for T2. So now I'm going to choose a different one. I'm going to choose T2 over here. Okay, and so the position at T1 is this. That's the position at time T1. And then the position at time T2 is this. Well, if you draw a line between those 2 points on the curve, then the average velocity is the slope of that line. What does it mean if between time 1 and time 2 your displacement is positive? What direction have you gone overall? Positive. Is that what you said? Okay, let's say positive. Let's say that you said that. Okay, so then if your displacement is positive, it means you might have gone all over the place, but your net motion was in the positive direction. Okay. If the displacement is negative, then your net motion was in the negative direction. And notice that, T2 minus T1, that always has to be positive, the denominator of that fraction. So whatever the sign of the displacement is, that's the sign of the average velocity. And so if you have a positive displacement, it means that your average velocity is going to have a positive slope. And if you have a negative displacement, your average velocity, that line, is going to have a negative slope. And so what that means is if V average is positive, the overall motion was in the positive direction. If V average is negative, then the overall motion was in the negative direction. So that's how, that's like, I guess, a first look at how direction comes into velocity. If it's positive, overall you're moving in the positive direction. You might have moved some in the negative direction, but you moved in the positive direction more than you moved in the negative direction. And if the average velocity is negative, then overall you moved in the negative direction. Okay, so now I'm going to use this idea of average velocity to define an instantaneous velocity, and that's the one that we care about. So for the instantaneous velocity, choose a single instant t. Remember, for average velocity, we had to choose 2 instants, but now we only have to choose 1. And then choose a t1 that's less than t and a t2 that's greater than t. Let's call this, so I'm going to do this in steps. So let's say this is step 1. Okay. And once you've done that, find the average velocity between t1 and t2. So I'm going to demonstrate this with, so my example function, the position as a function of time is going to be equal to t cubed. Okay. And the t, where we want to calculate the instantaneous velocity, is going to be 2. Okay, so for step 1, I'm going to choose a t1 that's equal to, a t1 that's less than 2, I'll choose 1. And a t2 that's greater than 2, I'll choose 3. And now we're going to calculate the average velocity between those two. So V average is the position at time t2, so position at time 3, minus the position at t1, so that's position at 1, divided it by 3 minus 1. Okay, so if the position is time cubed and time is 3, what's the position? Yeah, 3 to the third is 3, 9, 27. And then if time is 1, what's the position? 1. And then 3 minus 1 is 2. So you get 26 over 2, so 13. Okay, so now step 2, we're going to choose a new T1 and T2 that are closer to T. A new T1 and T2 closer to T. And calculate the average velocity. So this time I'll choose T1 equal to 1.5 and T2 equal to 2.5. And then V average is going to be the position at 2.5 seconds minus the position at 1.5 seconds divided by 2.5 minus 1.5. What's 2.5 to the third power? 15.63. And what's 1.5 to the third power? 3.38. What? Okay, yeah, that's fine. And then divided by 1. And so what do you get for that? 12.25. Okay, so does anyone have any questions about what I'm doing so far? Okay, step 3 is a long step. Step 3. Now, do step 2 infinitely many times. I don't know if we'll have time to do that before the quiz, but then the instantaneous velocity is what this sequence of average velocities approaches. So let's do it twice anyways, and we'll sort of see what's happening. What this sequence of average velocities approaches. Okay, so let's take T1 equals 1.9 and T2 equals 2.1.
Each time, are you supposed to get closer and closer to?
Yeah, we're pitching a little more each time. That's exactly right. So the average velocity with these two is the position at 2.1 minus the position at 1.9 divided by 2.1 minus 1.9. Can someone calculate that? No? Okay. 12. Is it rounds right to 12? Okay. Let's call it 12.01 for the sake of... and then we'll do another one. Say T1 is equal to 1.99. T2 is equal to 2.01. V average is equal to 12.00 something. You know, it's something getting closer and closer to 12 with each one of these steps. So you can say that the closer T1 and T2 get to T equals 2, the closer that average velocity gets to 12. Okay. So the instantaneous velocity is 12. That's the idea. We're never going to actually use this approach to calculate it, but that's, you can think of that as like the definition. And let me show what this does on a position versus time graph, so you can sort of visualize what a instantaneous velocity is. Okay, so position is on the vertical, time is on the horizontal. And this, if we're using the same function, the position is time cubed, so it's going to, let me just spread it out a little. Okay, let's say that. And let's say, I don't want to be too picky, but I want to show what's going on here. This meets at 0, 0. Oh. Yeah. And so let's say there's 1, there's 2, there's 3. Okay. So the first 2 choices of T1 and T2 we made were here and here. And so if I draw a line between these 2 points, that average velocity was the slope of that line. Okay. And then my next 2 choices were, let me label these, that's 1, 2, 3. So our next 2 choices were 1.5 and 2.5. And so our second average velocity was the slope of this line. And then our third set of 2 choices was here and here. And then our average velocity was the slope of this short blue line. Okay. And what we're doing as we pinch these 2 values together is the instantaneous velocity is the slope of the tangent line at that point T. It's the slope of the tangent line of the position versus time graph at the chosen time T. This isn't we don't use calculus in this class, but I know some people here have taken calculus 1. And if you have taken calculus 1, this way of thinking about it looks familiar, because all of calculus 1 is based on figuring out ways to calculate the slope of tangent lines. And that's what a derivative is. It's taking a derivative is a way to calculate the slope of a tangent line. And that's why calculus comes up naturally in physics, because we have these important things. Velocity is the first time you'll see it, that their definition is a derivative. And so anyways, that's we're not going to do calculus, but this idea of a tangent line is going to be important, and we'll keep talking about that. We're just not going to use the techniques of calculus to determine what those slopes are, you know. Anybody have any questions about that right now? What's a tangent line? Anyone have that question? Okay, so I thought you might ask that. So I don't really have a good answer to that. I should have trusted my instinct that you were going to ask that. So if you have a curve, a tangent line is a line that touches that curve and does not penetrate the curve at any point right next to it. Okay, so a tangent line at this point looks like this. It can, if this thing curved back down here, it's okay if that line goes through it over here. You just can't go through it right next to the point. Okay, am I going to use that wording? Yes, I am. A tangent line. Oh, do you have a better definition? Just a second, let me get this written down and then I want to hear that. So, tangent line. Is, what did I say? It touches a curve without passing through it near where it touches. Okay. Yeah, yes, and that's actually have you ever noticed, like, if you use a graphing calculator or something, you can, so if you look at a graph, so say you're looking at this graph on a computer or a graphing calculator, and you zoom in a step, okay? So now you don't see this whole thing. Your screen is taken up by this much of it, okay? And then you zoom in again, and your screen is taken up by this much. Each time you zoom in, that line looks straighter and straighter. The curve flattens out step by step. And this tangent line is the line that it's getting closer to as you keep zooming in. You don't like that? Okay. Don't use it. Don't use it then. Okay. Well, anyone who has a graphing calculator, try it, you know. Just look at some curve that's really has a lot of curvature and keep zooming in, and I'll be damned, it gets flat. Yes. Yes, that's true. Yes. You like that one? Okay. So let's talk about units. These are the units for velocity, This is average velocity and instantaneous velocity and distance. So the units are always a unit of length divided by a unit of time. And that means that in SI units, it's meters per second. And here's some things to remember about velocity. So notice. First, the instantaneous velocity is defined by a single instant of time, not two instants like average. Okay, so the instantaneous velocity is defined by a single instant t. And because of that, you can write instantaneous velocity as a function of time. You can't do that with average velocity. So because of that, the instantaneous velocity can be written as a function of time. And average velocity can't. And that's because you need two instants to specify an average velocity. The second important thing to remember about instantaneous velocity is it's by far more important in physics than average velocity. And so if a problem ever just refers to velocity, it's talking about instantaneous. You can always assume it's talking about instantaneous. If there's a problem that wants average velocity, it'll specify that. Okay. So velocity means instantaneous velocity. The third thing, the sign of the velocity, of the instantaneous velocity, is the direction it's traveling at that instant. So if a velocity is negative 50 meters per second, it means that at that instant it's moving in the negative direction. Okay. And the last one is the instantaneous speed, like what the speedometer reads. That's an instantaneous speed. Is the absolute value of the instantaneous velocity. So you can think of the instantaneous velocity as having a magnitude and a direction. The sign is the direction, and the absolute value is the magnitude. So if you're told that a car is moving with a speed of 30 meters per second in the positive direction, then the instantaneous velocity is positive 30. If you're told it's moving with a speed of 40 meters per second in the negative direction, then the instantaneous velocity is negative 40 meters per second. It's just a combination of that direction and that instantaneous speed. Any questions about that? Okay, well, let's stop there. That's where the other class ended. Let's just take the quiz. You'll probably be able to get out of here a little early. And then there's no school on Monday, so don't come here on Monday. And feel free to come to lab if you want to ask questions, but there's not going to be a lab for you, so don't come unless you want to talk to me about problems or whatever. Okay. Okay.